okay, which is essentially an int. Okay, so let's say that after these definitions have been made by the user, further on the user writes piece of code, and one of the statements in this in the code of the user program is t is assigned to this value test score n. Okay, so remember here that colon followed by equal sign is actually the assignment operator, and this assignment operator used in the programming language Pascal, while C had omitted this colon symbol, and therefore it just uses this equivalent as equal sign as an assignment operator. And initially when people write programs, they get lots of errors because they use this equal sign with the view that they are actually testing for equality of two different data values, while the single equal sign in C actually talks of assignment. And to check equivalence of two different objects, whether they have the same value, we wish to use this double equal sign, that is this equality operator. And that created lots of questions. And personally, for me, initially when we shifted to C from Pascal, there were lots of programming errors that got created because we used this single equal for checking equality when actually it meant assignment. And what is more confusing is that C also returns a value with the assignment operation, while language like Pascal doesn't return any value. So if since C returns a value, that value can be compared with the other value, and lots of confusions they create. So cutting all these things short. So this is this assignment operator, and let's treat it that way. So if we have this statement t is assigned to this value test score n, remember n is an integer, and t is a is this of type test score. So what should the compiler do here? Let me put this question. What should be done now? Should it be allowed just like that? So and remember this test score here is the name of the type. So essentially, it is actually the user wants to convert this input, that is the number n, into a type of with this name test score, and that value is to be assigned to this variable t. So this is this the type conversion operation that we all of us have used in C. So there is this conversion operation which is supported. So here in Pascal you can just say the name of the type followed by the object that you wish to convert, and then that particular object gets converted into this new type. So what do you think should the compiler do? Let me give you a hint out here. So first thing is, if we want to not surprise the user, the compiler should strictly do a runtime check to understand that this value of n, which is an integer and a signed number, so the value of n might be might not belong to the range of 0 to 100, and that is what is expected by this type test score. So before this assignment goes through, the compiler or the language implementation must check whether the value of n belongs to this range, and only if it belongs to this range, it should allow this typecasting to be performed, and then the value in that range can now be assigned to this variable. Okay, so here we need a runtime semantic check to see whether the value actually belongs to that range. So I think Nitin Kumar had asked this question: where do you need to make these runtime checks? So this is one example where you will have to make this. Now let's take the second statement, where we are doing the other inverse thing. So we are taking this variable t, which is of type test score, and using this typecast, that is to an integer. We want to convert that t to an integer and assign that value to this number n, which is of type integer. What should the language implementation do here? Is a runtime check required in this case? Correct, right. So all of you, many of you have understood this. So a runtime check is not required in this case. Why is it not required? Can anyone of you just unmute and speak? Yeah, range of integer int is larger, and there is no loss of precision. Yeah, test score is a subset of int, and that's that is what all of you have understood. So there is no check that is required since every test score is an integer. Okay. Now let's take the third statement, so which says R is assigned to this value, which is the type casted to this type long float, and the input to that is an integer, which is 32-bit, and assume this IEEE double precision form for long float takes 64 bits. So it's this longer version of the floating point numbers. What should be done here? Yeah, any idea what should be done here? Put zero after the decimal. Well, now let's take this case that this n is it's an integer and it is represented in the 2's complement form. Okay, and now we want to convert that integer in the 2's complement form to this IEEE double precision, that is 64-bit form. So how can that be done? Okay, so Nitin Kumar has asking, so a perfect conversion is possible. So what do you mean by perfect conversion here, Nitin? Can you unmute and speak? No digit is lost. Uh, Still, I'm not really convinced. Let's say the number that I want to refer to is, let's say, 153. So n has a value 153, which is represented in some in the 2's complement form. How do we convert it into this floating point number? Okay, so f is that's what Nitin Kumar is saying. So f is represented as 0.153, and then we get this exponent 3. So the binary equivalent of 3 is put in the exponent form, and this 0.153 now needs to be represented in this in the mantissa or the significant. So we write the binary equivalent or the bit pattern corresponding to 0.153. Excellent, excellent. So you have got it. You got it. Right. So this conversion, is non-trivial. It's not a straightforward way with which this 2's complement number is kind of is to be converted. Consider the situation that n is a negative number, say minus 153. Then it has this 2's complement form. Okay, so the sign bit of the corresponding floating point number must be set to 1, and we now need to have the same 153 representation, the bit pattern corresponding to 153, which has to be extracted from the equivalent positive representation from the 2's complement form. That will give us this value 153, and therefore that needs to be populated in the significant or the mantissa of the floating point number. The exponent remains 3, right? So this is this non-trivial conversion which needs to be done at runtime. Okay, and that's what is supposed to be done. And the compiler now needs to insert code. Some code instrumentation, as it is called, is required. So because n is to be treated, is taken up as a 2's complement number of size 32 bit, the compiler now needs to check that whether n is positive or negative. And then if it is positive, then just take the bit pattern and convert it as we have discussed just now. And so in the memory, we write a bit pattern of 64 bits now, because this is a long float, and the 64-bit bit pattern which we have discussed would be something that Nitin Kumar has actually stated. And if it is a negative number, then the compiler should fetch the equivalent positive number out there, make this conversion into the floating point form as we have discussed, and put the sign bit of the corresponding floating point number as 1. Okay, so this 32-bit number is now converted into a 64-bit number, a 64-bit entity, and this 64-bit is actually interpreted as a double precision floating point number. Okay, so that interpretation is done by the compiler. That's the language implementation, compiler or the interpreter. Inside the memory, those are just bits. So the CPU doesn't know that this is a floating point number or an integer or just a character string or anything of that sort. So it is for the programmer and the language implementation to understand that this is actually a particular type and it has to be represented in a particular way. Right. Let's take the next statement. This is n is now assigned to integer r. So r is this long float type, so double precision, real number, and that is now to be typecasted into an integer, and the value is to be assigned to n. So how would this be implemented? Yeah, any ideas? Discard the decimal part. What is the decimal part? Remember that inside the machine, it's all binary. The decimal equivalent that we are writing on the screen is for us, for our understanding. The computer doesn't understand decimal. It is working only with binary. And as we have discussed earlier, the decimal point, as we say, the point is actually implicit inside the floating point representation. So that is implicit, and it also makes sure that the first bit after the decimal point is always 1. Okay, Vishaka is saying convert the mantissa exponent to an int. Yeah, correct. But how would we do that? Okay, Nitin Kumar is saying that if the value of r is within the range, And if it is outside the range, when will we know? It's a very tricky question. But let's assume that if it is within the range, then we now need to truncate that float into an integer, which is the closest representation of an integer number given this float value. And that's perfect. That's the answer which I was looking for. Correct. So we have to now, the compiler, we mean the sense the language implementation now needs to check what is the value of R and which is the nearest integer that is representable for this value R. So get that integer, represent it in the 2's complement form, and store that bit pattern in the memory location specified by n. Okay, and if R is not within the range which n has, that is n is a 32-bit entity while R is a 64-bit floating point number, so there is an exponent component also out there, and therefore if we combine these two, it might just happen that the nearest integer cannot be represented using 32-bit. Then what should we do? Should that be flagged off as an error if it is beyond the range, or should it not be flagged off as an error? Okay, Pulkit is saying that it should be flagged off as an error. Yeah, it is an overflow situation. So the question is whether the overflow should be treated as an error or it should be silently, the compiler or the language implementation just tries to do its best and leave it to the mercy of the programmer to understand what needs to be done. Well, strictly speaking, I agree with Pulkit that it needs to be flagged off as an error if it is beyond the range. Okay, so that is what is written out here. So this particular thing requires a runtime conversion, of course, and also a check that it is within the range. It might be an overflow, or it might also be an underflow. Okay, and if it is an overflow or an underflow, the language implementation should flag that as an error and terminate the user program. Okay, this is some sort of a runtime error that has happened. Okay, and if it is within the range, then as Nitin Kumar said, we can make that conversion and create the bit pattern for n, which might be entirely different from the bit pattern for R. Okay, and the value also would be little different. We are trying to represent it with an integer as close as possible. Correct. And here I would like to pose a question. So, what do you think does the C programming language do for this kind of a situation? So that is where n is assigned to integer r. So that is the real number, or a double is to be converted into an int using this typecast operator. Does the C programming language flag as an error if there is an overflow or an underflow? Does it flag an error? Yeah. So great. Nitin Kumar actually tested it out while we were discussing, and Prabhav has probably not tested, but he knows the answer that it is left to the programmer. There is no error that is given. And don't you think that is strange? Okay, we have argued that it should be flagged off as an error, but the C language implementation does not give it. Okay, fine. So yes, Nitin Kumar probably has written a C++ program. I see C out and less than all that. So even C++ does not actually, give out an error there. So not just C, even C++ is also not strongly typed, and that's what we mean by strong typeness, which which we discussed during the start of this lecture. So now actually things are becoming more clear now. The output, with that such a big number has come out to be some nonsense value, and the programmer is at the mercy of the language. Okay, so both C and C++ are not strongly tied. But now I ask the question, why they made that kind of a decision? Why didn't they flag off an error? Okay, correct. Correct. It is essentially for efficiency. Okay, what kind of efficiency? Well, here the check actually is to be done at runtime. Okay, which slows down the execution speed of the program. So, for the sake of efficiency, they decided to do away with the check. And as Pulkit says, they relied more on the programmer's wisdom rather than making those checks themselves. And all sorts of errors might happen if this can really surprise the program. Fine. So that's good. So and then, some strongly typed languages do make this check at runtime and then flag it out as an error. Okay, and therefore debugging the program is easier and it is more maintainable. Okay, and probably it might run as slower, but then this is the more recent way with which language implementations uh, implement these programs. So they actually make these runtime checks so that there is no surprise, because over time people have understood that maintaining a software is more costly and more difficult than actually this issue about efficiency. So again, a design decision. If the piece of code actually is running, in some application which is having a hit of 1 million hits per second, then absolutely I want efficiency to be done out there. And then we hope that the program does not have these kinds of issues, that there is an overflow or underflow or things of this sort. So in that case, we come out with a compiled version, and that's what C and C++ languages are meant to be, are meant for, to generate efficient code. But if the application program is, let's say, executed once every hour, well, it doesn't really matter whether it takes 10 milliseconds or 30 milliseconds to give its response. It does not really matter. So in that case, I think the language design should make this check at runtime and therefore save the programmer from some sleepless nights. Right. Let's take the next statement here. Here, n is converted into an integer from this type C, which was this enum of type Celsius temperature. What should be done here? No check required. Correct. So Vishaka is right. No check required. Celsius temp is just another name for int. So nothing needs to be done. So no runtime code required. No check required. And what about this other way? That is, C is assigned to Celsius temperature n. That is, the integer n is typecasted into this type, which is Celsius temp. Well, here also no check is required, because Celsius temp is just another name for integer. Nobody put any range bounds out there. So here also no check is required, because it is essentially a different name for integer, right? So these examples actually gave you various situations where these runtime decisions have to be made by the compiler. And I hope now some of the questions which Nitin Kumar had raised are they addressed now? Yeah. Okay. Fine. We will see few other examples also, probably not in today's lecture. Then again, we will have a discussion where we would see that the knowledge about the representation of numeric types actually comes out helpful in those situations. So we will take it up sometime later. I think we are almost out of time, so let's just stop here. We will see this the rest of the slides from next lecture onwards. So we have a couple of minutes. If there are any questions, please unmute and ask or type them on the chat window. Otherwise, we will end the lecture now. So if there are no questions, shall we end the lecture? Okay, fine. Thanks.